If I can have your attention, everyone, we're going to start the seminar now. It's my pleasure to present Maritza Lara-Lopez, who's currently at AAO in Australia. And she's going to talk today about the star formation rate, metallicity, and mass.
Hi, thank you. Welcome, everybody. It's a pleasure for me to be here. Well, I'm going to talk about star formation rate, mass, and metallicity relationship in star-forming galaxies using large surveys. So I'm going to show results about the GAMA survey and the Sloan survey. Well, basically, I've been working now, this is my last year in PhD and now in my postdoc, about the relationships between these three fundamental parameters of galaxies. So there is, sorry? Okay, I can wait. Well, first of all, I'm going to talk about the mass-metallicity relationship. So this is a really well-known relationship. It was discovered in the 1979 and confirmed in the 1981 by these authors. So since then, it's been widely studied because this relationship it's important because it's telling us that the metallicity and the stellar mass of star-forming galaxies is closely correlated. So we have that massive galaxies show a higher metallicity than less massive systems. Well, this relationship is well established in the local universe by the work of Tremonti in 2005 using Sloan data. This is their mass metallicity relationships. So we can see here clearly that for massive galaxies we have a high star formation rate, a high metallicity, sorry, than for less massive systems. So this work was done by 64,000 of galaxies using Sloan data. There are two main ways to explain this relationship. So one, it's due to metal loss, and baryon loss from gas outflows. So this context is telling us that small galaxies here has lower gravitational potential, so they cannot retain their gas. So due to supernovas and gas outflows, they are losing a lot of baryonic material. So they are losing their metals, and they cannot reach higher metallicities than, for example, massive galaxies which have a stronger gravitational potential. They can retain their gas. Their gas is again reprocessed, and they can reach higher metallicities. So this is one well-known and very logic explanation. Another explanation is the downsizing. So downsizing is telling us that lower mass galaxies form their stars later and on longer time scales than massive systems. So in this way, it's like if massive galaxies would form their stars quickly than less mass galaxies. So these galaxies are taking their time. They are forming slower. Their materials, they are evolving slower. And so they are reaching, at the same time, they cannot reach higher metallicities than, for example, these galaxies. So this is about the first fundamental relationship. So now I'm going to talk about the second one, the stellar mass and star formation rate relationship. So this relationship is also well known. It's just stellar mass versus star formation rate. So we have a pretty strong correlation here also. With, again, lower mass galaxies are showing lower star formation rates than higher mass galaxies. So here we have a main sequence, which was identified, it was identified previously, but it was confirmed by Noeske in 2007 at several redshifts. Well, one problem here to interpret this physically is that if we have low mass galaxies, they also will have a lower H-alpha emission, so they will have a lower star formation rate. So to think of this in a more physical way, we need to work with a specific star formation rate, which is the star formation rate divided by the stellar mass. So this is going to tell us the star formation rate per unit mass. So this is a more physically way to see this relationship. So if we do that now, what was a correlation here now becomes an anti-correlation. So this is telling us that low mass galaxies actually are having a highest star formation rate per unit mass. So these galaxies are more actively forming stars than, for example, high mass systems, which it makes sense actually with the downsizing, because these galaxies has already process all their gas. So these galaxies have processed their gas. That's why they have higher metallicities. However, low mass galaxies are still processing their gas, so they have a higher specific star formation rate and a lower metallicity. So it makes sense in the context of downsizing. This also is a figure by Noeske, 2007. So we have these two relationships well known, both have been widely studied in several years. But there was a third relationship which I didn't find anywhere. I was at this time in my last year of PhD. So the metallicity and star formation rate relationship was not previously studied. I was surprised of that, so we worked on that, and we found this. Actually, we found that it was not studied before because the correlation is not so strong than in the previous cases. So anyway, we see a correlation. Star formation rates tend to increase when the metallicity increase. So we published this in 2010, and at the same time, Angel Lopez Sanchez also published the same. So again, the relationship is not pretty strong, but it's there. So at this point, we have field in this triangle. So we have three relationships. We have two relationships close correlated, tight correlations, and we have a relationship that it's dispersed, that it's with a high dispersion. So this if we think this in a three-dimensional space, we have two variables that are closely correlated and one that's not correlated. So that could be the clue. That was the clue for a more general relationship. And so we found that there was a plane. We found a plane for making these three variables in a. Okay. So we plot those three variables in a cube in a three-dimensional space, and we found a plane. So what are we seeing here with these three relationships? Mass-metallicity relationship, the mass star formation rate relationship, and the metallicity star formation rate relationships. Actually, those three relationships are just the faces of a plane, are the projections of this cube that we have in three dimensions. So we found that we can express the stellar mass as a function of the other two. So that this is important because now we have two variables, we can know the third one. And we apply this formula, we fit a plane in three dimensions. We apply this to our whole Sloan data. So we found that we can reproduce the stellar mass of the entire sample, more or less with that. The dispersion here, it's at least 30% lower than in any of those cases. Also, we work with high redshift data. So here in blue, we have data from AIR 2002 at redshift 2.2, and the red ones are data 3.5. So in this data, they are high redshift data, so there are galaxies that present evolution. So we have a very strong metallicity evolution. We also have a very strong star formation rate evolution. And in this case, both variables are evolving, so the evolution is in this way. However, when we fit the plane, and if we fit those data also to our plane, they are there. They just fit the plane. So we were surprised about this because we are not finding any evolution in this plane. But also it makes sense. Why? Because here we're expressing the stellar mass as a linear combination of metallicity and star formation rate. Now, metallicity is evolving toward lower values, while star formation rate is evolving to higher values. So if this is going up and this is going down, so sorry, if this is going down and this is going up, so this difference, when you do the linear combination, it doesn't matter. So again, I can reproduce the stellar mass of this of even higher redshift galaxies up to 3.5, finding not evolution. So this is the plane that we found, and here we have the high redshift data, and here is another view of the plane, more or less in the face-on view, and here the high redshift data fit the plane. So now I'm going to talk about the work that I'm doing in Australia. So I'm still working on these relationships, but now using two big surveys. My PhD thesis was about Sloan survey. Now I'm working with the Sloan survey and with the GAMA survey, which is a deeper survey than Sloan. So the Sloan survey, we have that it accounts for at least 1/4 of the sky. So it is using a 2.5 meters telescope, which is located at the Apache Point Observatory in New Mexico. It's using optical fibers to take the spectra. And this is the telescope. So this survey, it's a huge survey, everybody knows it. It's been working for more than 8 years now. It's free to the scientific community, so this is great because we can use it. It's accounting now for more than 70 PhD theses, just including the students that are working with direct collaborators at Sloan, so there are even more theses on this. By 2008, the Sloan has accounted for more than 2,000 papers in referee journals with more than 70,000 citations, so it's a really important big survey. Now I'm going to talk about the GAMA survey. GAMA stands for Galaxy and Mass Assembly Survey, so this is the web page. Now we have the first data release. Now it's available on the internet, so feel free to visit this web page, and you can use now our data. The GAMA survey is using the Anglo-Australian telescope, a 3.9 telescope. It's located in Coonabarabran in Australia. Here we have the image of the telescope, and it's a shame that you cannot see it, but here you can see two kangaroos. They are everywhere there. Here I have another one with the Magellan Clouds, but you cannot see it, unfortunately. Well, this telescope, it's using an instrument to the F and AA omega. So this is a robot that positions optical fibers in the coordinates that you give it. So it was really expensive, but it's really fun because you can have the configuration you want at the moment. It's using also optical fibers as a Sloan. The diameter of the Sloan fibers is of 3 arc seconds, and the one of GAMA it's 2 arc seconds. So this is useful in the case of clusters, for example, because for GAMA we don't have much problems for collisions of fibers. So there's a large project now on clusters of galaxies using the GAMA data. Now, if we see the sky, the Sloan data, it's the black dots here, and the GAMA regions are these ones, G9, G12, and G15. So it doesn't look much, but the Sloan, the GAMA data now it's accounting for more than 140,000 of galaxies, emission line galaxies. So we have a really large data set. It's not the 900,000 of galaxies that Sloan have, but I mean we have enough galaxies to make a good statistic and a good study. Now, for the work that I'm doing now as a GAMA collaborator, I'm working with the Sloan data and with GAMA data. So for the Sloan data, I'm using data from the Max Planck Institute and Johns Hopkins University, the Garkin data. So to work again in these relationships, I'm going to use the star formation rates from Brinkman 2004, metallicities from Piemonte, and stellar masses from Kaufman. So those are estimates that are Bayesian estimates. So they estimated their properties statistically using photoionization models, and they do it for one galaxy. So this is the closer way that we can have a really accurate estimate for single galaxies. Otherwise, you will have to apply one formula for the whole data set, and the scatter is going to increase. So those are really robust data, so I'm pretty happy. For the GAMA survey, we are using Gandalf data. This is the pipeline. We're analyzing all over spectra with this. And so we're estimating star formation rates following Hopkins 2003, recalibrating to these ones to match our data. And again, metallicities with this method, and we're recalibrating it to these metallicities. And the stellar masses are based in this paper, and they agree with the Garkin measurements. Now, as usual, we're working with star formation rates and metallicity, so we need star forming galaxies because AGNs follow difference, are more complicated. So we are selecting star-forming galaxies. The gray ones are Sloan data, and the red ones are gamma data. So we are only keeping these galaxies. Well, if we compare both star-forming composite and AGN galaxies, we can see that we have more star-forming galaxies in the gamma data and a bit less AGN and composite objects, because gamma, it's a deeper survey, so we would expect that that our number of AGNs will decrease. Now this is a plot showing the redshift and the absolute magnitude for Sloan and for gamma. The red line here, it's exactly the same that this red line here. So we can see that gamma, it complements perfectly Sloan. The galaxies that you see here in the Sloan, you don't have spectra. So this is just the image. So actually gamma, it's based on Sloan. Gamma, it's taking Sloan targets, and it's taking the spectra of those targets. So gamma, it can be talked as a complement of the Sloan survey. So we have now we have all this now taking into account Sloan and gamma. We have a really huge data set of galaxies. So for this study, I'm dividing all this sample in volume limited samples. So I'm working with these small boxes at the same redshift and with similar absolute magnitude for Sloan. And I'm doing the same box for gamma, using the same redshift ranges, but in this case at a lower absolute magnitude. So the colors are the same in both cases. So here, every box, this is, for example, the mass-metallicity relation, and every box here corresponds to one box here. So the first two boxes, I don't have gamma data, so here I'm presenting just Sloan. The third one corresponds to the blue one here. So in the third one, I'm going to plot this volume limited sample and this volume limited sample of gamma. So in this way, I have 16 volume limited samples accounting for both gamma and Sloan. So we can see here the mass-metallicity relation for a really complete and very large survey. Now, I was expecting at the beginning that since the gamma data it's a deeper survey, maybe I will have lower metallicities because are fainter galaxies. But I was surprised that actually it's not. So gamma data follow perfectly the mass-metallicity relationships. I didn't find any kind of evolution or any kind of different property of of fainter galaxies. So, but actually this is telling me that this relationship actually is fundamental. It doesn't matter if the galaxy it's faint or if it's bright. It's that galaxy is going to be always here. So so we can see that both surveys complement each other. When the Sloan survey lost completeness here, gamma survey is here, and in all the volume of the samples we can see the same. So one important thing of gamma is that the Sloan galaxies I don't have Sloan galaxies in this redshift, for example, at higher redshift up to 0.36 is the highest redshift that I can have with gamma and Sloan. So I don't have Sloan galaxies here. I have just a few, but I have enough gamma galaxies to measure properly evolution. And actually, we found that here we have the 16 samples, and here in the left panels, I'm showing I'm concatenating all the samples. So all these 4 samples are here, all these 4 samples are here, the same for the others. So this is just to generate a more robust sample and to measure evolution in a more robust way. So here I found actually that at least 0.1 x of evolution in metallicity. And I'm doing this now with a very, very large statistically significant sample. So we found this for this sample. For the mass-metallicity relation, the same. When Sloan lost completeness, I have gamma here, so I can extend this relationship to lower mass galaxies at every redshift. And we found that a really high evolution here of star formation rate, almost 1 dex. And well, the mass-specific star formation rate, I'm pretty happy with this because it's really tight. And the evolution it's even stronger, more than 1 sigma. And yes, well, we are finding the same low mass galaxies have higher specific star formation rate. They are forming stars, and for low luminosity galaxies, we have exactly the same behavior. So the slope is not changing. In this case, we are just fitting the 0 point in our relationships. And so the evolution, and the last one, the one that it's highly dispersed, and we don't have a really tight correlation. But anyway, we did it because it's the third phase of our cube. So here the dispersion is pretty high, especially when we see both samples together. But anyway, more or less, we see that the formation rate increase with metallicity, and we are not measuring here an evolution, anything. Well, when we analyze our sample and we found this value, so we have evolution of metallicity up to 0.13 in this volumetric sample, and a most robust evolution of 0.07 in metallicity. So it's not much, but actually it's in agreement with models and with previous results. The star formation rate it's stronger, and the specific star formation rate it's even stronger. So this is the results that we found in this topic. And now I also work with the fundamental plane now for the gamma sample. So we did a 3-dimensional study. In the gamma sample, our sample it's a bit the dispersion it's higher, but anyway, it fits with the Sloan plane that I found previously, which is tighter. And now, if this is a plane, I can. This is here. This is the plane that I found. So this is mass metallicity and star formation rate of Sloan galaxies. Everything plot in a cube. So this is what I fit. This would be the mass metallicity. The mass metallicity relationship. Yes, this is the one that I show you. This is the metallicity star formation rate, the one that is more scattered. And the last one should be here. This is stellar mass versus star formation rate. So the plane that I'm finding it's there. If we can project this plane in the star formation rate, in the mass star formation rate relationship, and if we do that, we do this projection, we find this. So the lines correspond to the projection, and the dots in this case corresponds. I'm doing beams in star formation rate, and for every beam on the star formation rate, I'm doing medians of metallicity in stellar mass beams. So I'm doing 3 beams here. I'm finding this relationship, so I can feel all the relationship, and I can also project the plane over these relationships, and it's in good agreement, I think. This is for 3 volume limited samples, the concatenated ones, up to 0.33. So we find this part it's evolving, but it doesn't matter. The plane more or less fits to the whole relationships, and every one of these is volume complete in volume. So it's the most robust that we can have. Now, I would like to talk now about about my last year of PhD, because we published this. This was my last paper here. It was a letter, but at the same time that we was publishing this, there was another paper that appeared exactly at the same time at the same moment, finding more or less the same result. In this case, they call to these 3D relationships a fundamental metallicity relationship. This is a work made by Vanucci, 2010, In this case, in my case, I'm expressing the stellar mass as a function of metallicity and star formation rate. In this case, they are taking as a principal component the metallicity, and they are expressing the metallicity as a function of the stellar mass and star formation rate. But if you do that in that way, you find a surface. So now, is it a surface or is it a plane? So I've been working on that also. Before that, I would like to do a parenthesis, a huge parenthesis here, because what to do if you submit a letter and it takes 20 days to find, just to find a referee. So we had a lot of problems trying to publish this. So when finally a referee accepts, the Manucci's paper appeared on AstroPH, and at that time that paper was not accepted. So then our referee was trying to stop our publication. We changed our referee. The second referee was exactly the same. Then there was a problem with the editor also, another Italian. And so we had to change of editor. We had to talk to the editor-in-chief. In this case, Jordi, my boss, did it for me. So we have to also involve the Spanish representative of Astronomy Astrophysics in 2010. At that time, it was Fernando Moreno Incertis. Now I don't know who is the representative. So we had a lot of problems, really a lot of problems. But what my recommendation here is to fight and don't give up. At the end, we changed our editor, and Claude Berthoud, the referee-in-chief of Astronomy Astrophysics, was our new editor, and he found us an objective referee. And at the end, our letter finally was accepted, but it was really, really difficult. So just for the existence of this other paper, I don't see any problem. I think that you can publish two papers showing the same result, and I don't see problems actually. But anyway, now I'm studying also these relationships because I was worried it could be a surface. Maybe I did it wrong. I didn't know. So I apply a even more robust analysis. I use PCA, principal component analysis, and I discovered actually that this relationship is wrong. So now I'm calling this a misleading fundamental metallicity relationship. So we have submitted, so when you are working in 3 dimensions, well, first, Manucci, what did, it's just to make a grid in one of the faces of the plane. So when you're working in 3 dimensions, you cannot work in 2 dimensions. You need to take into account the whole space. So you need to do a proper 3-dimensional analysis, and if you do that, I did PCA and I found that I can reduce the dimensions to only two dimensions, so a plane. But if I work with the procedure of Manucci, I can find actually his surface. Yes, there is a surface if I apply his method. However, this surface, and this is the plane I found. So we match more or less in this region. However, if you put all the data above the planes, above the the plane and the surface, I found this. So actually, the surface become curved when you don't have data. So this part that is poorly sampled, it's making this surface curved. So, but that is because you are working in 2 dimensions, not in 3. And yes, so this surface just don't fit the data. This is the face-on part of the view. So this is the part that is most scattered. So it's more or less the star formation rate and metallicity phase, but it's not that phase anyway. But it's close to this part. When you do the principal component analysis, I found actually that the most active, the principal components were closer to the metallicity and to the star formation rate. So what I can do is to express the stellar mass function of those two, but not the metallicity. If you make things wrong, you can find this a curvature. I mean, I can find the curvature. He did. I can reproduce his method, but it's not correct for a 3D study. So I did this analysis. Yeah. Also, I also work with the metallicities of Manucci of this paper, and I found that Sloan is accounting for a lot of emission lines. You can measure the degree of ionization of the gas. You can apply a very robust metallicity indicators, and for all of them, Manucci is using this one. So he's using the R23 and the N2 method. The N2 method, it's well known that it doesn't work for metallicities higher than 8.8. So this part, you can see it, it's almost vertical. So you don't have any relationship here. And if you do that, if you apply this method to estimate metallicities, you find this. So your metallicities higher than 8.8 are useless. You cannot use this method. The R23, you can use it, but anyway, the expression is higher because he's not taking into account any degree of ionization of the gas. And so he's using an average between these both, and just if the difference is lower than 0.2 or something. So that reduces the scatter, but in a more no proper way. And so this is the last result. But anyway, the residuals are pretty high, but just to use this method for the high metallicity regime, it's incorrect. And also, if you do that, the mass metallicity relation, the curvature becomes even more curved. So probably that's why his surface was even more curved than what it really is. But just because the metallicity, it was not properly measured. And I already talked about that. The principal component analysis. Now, there is something that I would like to emphasize here, and it's that the mass metallicity relationship is curved. I have treated a second order polynomial. You have seen it. Now, it was a bit a puzzle. How can something be curved and be flat at the same time? So at this time, I was coming here and I was buying souvenirs, and I saw this. I'm living in Australia, so this is the perfect example of something that it's curved and it's flat at the same time. So I think it's a good example. So if this is the mass metallicity relationship, you can have something curved. You can have in a plane any kind of shape. So you can have a curvature here, but at the same time, it can be flat. It can be in a plane. So my boomerang actually would be more or less in that phase that I'm showing here. Yeah, so we have submitted a letter to Martina. Now showing all this analysis of metallicities and of the three-dimensional study that it was not properly made before. So my conclusion is that it's a plane. I don't see any curvature. I don't see this surface. I can reproduce it, but it's not properly done. It was not properly done. So we have submitted this. So my conclusions about this is that because it's the main problem. We have two main problems: the metallicities that they were not properly estimated, and the other problem is that the way in which those authors are working in 3 dimensions is not correct. I think I'm finishing here. Yes, that's all. Thank you.
Thank you very much, Maritza. Does anyone have any questions?
So the main difference of your work with Manucci was you used a different calibration of metallicity, or your data was better, or can you explain? I'm not really understanding.
What did you don't understand?
The main difference between the estimation of metallicity which you did in your work and
well, I'm using Bayesian metallicities. So those metallicities are based on statistical methods, so they are pretty robust. But at this point also, I have played a lot with different metallicities and with different star formation rates. And if you do a proper estimation, it doesn't matter which method you are using. You find this plane The problem is if you use a method which doesn't work for high metallicity regions, as is the N2 method, for example. If you use a method that you cannot use, so that's when you are having problems. But I have reproduced this, for example, using, this is a Tremonti metallicity that I'm using, Culian Dopita 2002, Pettinian Payel 2004. In all the cases, I'm finding more or less the same dependencies. Here, it's the scatter, it's higher, but it's the same. I mean, the main problem here with those metallicities comes when you are using these metallicities. These metallicities are, you just cannot use that for anything.
In a sense, a PCA will allow you to quantify how close to a plane is the distribution.
Yeah, actually, sorry, I didn't mention that, but when I did the PCA analysis, it gives you a number. So it gives me that the 98% of the variance can be explained by a plane. So it's only 2% that is the scatter that you are seeing.
Yeah,
Anyone else?
So other authors, Yates and Otta, say that for low gases, the relation between the star formation rate and the metallicity is opposite. I mean, when the star formation rate is higher, the metallicity is lower.
Yeah.
Could you see this also in your data?
Yeah, actually I do. Yeah, well, this is my letter. I'm in touch with Yates actually for his work here. The main problem comes with these relationships, the one that present the higher scatter. So, as we saw, it's really important in the way in which you are binning. So this relationship, basically, you see that as star formation rate increase with metallicity. That's the general relationship. It's the scatter is high, but that's the tendency from the whole relationship. Now, it's also a puzzle. If you start binning in metallicity, and if you estimate the median star formation rate per bin, you find this, which is what actually I'm doing. So in my bins, you see the dots. More or less, you see the same tendency, star formation rate increase with metallicity. However, if you do the opposite, if you do bins in star formation rate and estimate the median metallicity, you find the opposite behavior. So in this case, it's anti-correlated star formation rate with metallicity. So it's really incredible how does it change depending on the way you are binning. But again, this if you do that, if you estimate bins here, every dot here, the sigma is going to be incredibly high. So I wouldn't do that. That's the main difference between also the work of Mannucci and mine. The sigma of Mannucci, it's really high. It's pretty high, especially in the part that it's cured, and that is shown here. The sigma, it's high. That's the difference between these two works. So I wouldn't. Because you're saying star formation rates should increase with metallicity. That's the tendency of the general relationship. But if you do a wrong bin, you find the opposite behavior, and that has several implications in the physical explanation that you are giving. So I think it's important to at least to plot the data and to see that your fit is matching with the data.